So it's my great pleasure to introduce Dr. Jan Moritz Joseph for giving a guest lecture today. So Dr. Joseph, received his PhD from University of Magdeburg in Germany in 2019. He worked on the topic of networks on chip for heterogeneous 3D systems on chip, and he's actually going to talk about some of that today. His PhD was actually awarded the Summa Cum Laude, which is one of the highest honors you receive for your work. He also received the award for the best PhD thesis in ECE from his university. Of course, my interaction with Moritz goes to 2019 and 20 when he was actually a visiting researcher at Georgia Tech. He was visiting my lab, and he was here for about, I think, 8 months, if I remember correctly.
6 months actually only, yeah.
And actually, in some sense, Moritz arrived at a good time. This was pre-COVID, so I remember kind of Moritz and I going for, I think, lunch. That was probably early 2020, and then things went south right after that. And so currently he's at RWTH Aachen University since middle of 2020. He's been working as a postdoctoral research fellow. His broad research interests are in NoCs, of course, and more recently he's been looking at again NoCs for ML accelerators, neuromorphic computing, and simulation. And some of these are things he'll also touch upon towards the end of his talk as he introduces some project ideas. And so with that, Moritz, again, thank you so much for doing this. I'm actually somewhat multitasking here. I'm attending like a PC meeting right now, which is kind of also why I requested you to give this lecture. So I'm actually going to be on mute and with my camera off on this screen. So for the students, please feel free to interrupt and ask Moritz questions. So Moritz, typically I know some of the students just write questions on chat. So what I would encourage you all is, because Moritz is presenting, he might not be monitoring the chat, right? So please go ahead and ask your questions in person. In case there are some questions on the chat, Apurv, I'll request you to just monitor the chat and just interrupt Dr. Joseph and ask him the question on behalf of the students. Okay, so with that, let's get started. Moritz, the floor is all yours. Thank you.
Yeah, thank you for the very kind introduction. And welcome to the lecture today. So the focus of this work will be on two specific pieces of work regarding network on chip for heterogeneous 3D integration. And the topic that I want to touch on is bridging the frequency gap in NoCs. So that's a specific property that you only see when you use heterogeneous 3D integration, that there's a specific frequency gap within your NoC. And this is a huge design challenge, and you have to tackle this. And I'm going to just show two examples of my work, how we are approaching this problem, both from a network architecture point of view, but also for router microarchitecture optimizations. And okay, so let's take a look at the agenda for today. So I'm first going to start with the introduction of the topic regarding heterogeneous 3D integration, and give a very short and brief introduction into the technology aspects of heterogeneous 3D integration, give an example why you would like to do this, and what the advantages and the most daring challenges are for these settings. Then afterwards, I'm going to go into the more interesting part for you guys, specifically NoCs for heterogeneous 3D integration. And there I'm going to show that homogeneous architectures will yield varying costs, which is not always the optimal point here. And this has consequences on architectures and on EDA. And within this talk specifically, I want to focus on this frequency gap that I already talked about, that limits throughput and that is also exploitable to do latency optimizations. And as I said, there is this frequency gap. So let's go into the details of the two ideas from an architectural point of view that I want to introduce. To solve this, the first one goes into the direction of the co-design of routing algorithm and router architectures. And specifically, I want to introduce some models, like a modeling approach that I did to prove the idea, then give you ideas about the architectural properties of the routers, and finally give a short overview of the results, of course. And then I'm going to introduce a second approach to the same problem. And here we are not working on this co-design of routing algorithm and router microarchitectures, but rather we focus on heterogeneous network architecture. So we broaden the scope and also find a quite nice solution for this with quite good results. And yeah, finally, as I already said, they're going to be like an idea for the class project, which is on NoCs for data flow-based DNN accelerators. Okay, let's start with heterogeneous 3D integration. And just like a short motivation for you, if you have any questions, just raise your hand. I can see it here actually on my screen, so my setup is okay for that, or just interrupt me by just asking right away. That's all right. So heterogeneous 3D integration is basically the technological background for everything I'm going to introduce. So it's quite important to get at least an idea of what are the most important challenges here. So you might all have heard about 3D integration. 3D integration is a topic that has been, well, in research, I think for more than 20 years now, probably more than 30 years. And it is also now finding its way into like actual chips that you manufacture, and you will find quite a lot of research on that. And the idea of 3D integration is that you can do a vertical integration and a vertical interconnection. So that's basically what is also shown here in the middle with this nice, very simple pictogram, that you have dies of chips here, chip dies. There are some components integrated, and then I also already showed a network on chip here, or like any interconnection infrastructure. But the basic idea is that you have multiple of these dies, and then you stack them, and you also vertically interconnect them here. And for 3D integration, there are two main principles how to build these systems. So the first one is work now? Yeah, now it works. So the first one is that you can use stacking of dies. So here's basically the idea that you manufacture the dies individually, and then after you have manufactured each individual die, you stack them on top of each other and glue them well to their neighbors. And then by that you have a stack of dies which have been manufactured at different locations with different vendors. Like in theory, that's the idea here. The second approach is monolithic 3D integration, and this is the more challenging part actually, and also the more modern integration approach, where you build the whole stack from bottom to top monolithically in one approach. So that's the more challenging part, because then you have to basically make sure that you can manufacture this whole 3D stack at one manufacturing plant in one process. And both these approaches require different vertical interconnects. So for stacking of dies, as I already said, what you're going to do is you're going to have individual chip layers, and then you stack them on top of each other, and you glue them. You keep the bottom one and you glue the top one on top of that. And so how can you interconnect like these two layers now? And the basic idea here are these through silicon vias, and what you do there is you etch a hole from the top layer to the bottom layer, and then you fill conductive material into this hole. And this is a very disruptive process, of course. And what the consequence of this disruptive process is that you will have a large area requirement for these TSVs. Because, quite simple, that things that are in close proximity to this TSV that you have manufactured, they are most of the time damaged, and this is why you have these so-called keep-out zones, so zones within your IC that have to be kept free of transistors and other functional components, so that they are not getting damaged during the process. So this is a really challenging process in terms of that. You are destroying parts of the chip if you don't have these keep-out zones, so TSVs are really costly in terms of area. Monolithic intertier vias are now the counterpart to that. So if you're monolithically integrating the whole chip, you can directly manufacture these vias. And by that, these monolithic intertier vias are better in terms of they require less area, and they also have better electrical characteristics, but they are more challenging to manufacture. So this is like the very broad landscape of manufacturing in 3D. And let's just, from a very high level point of view here, more from like an architectural point of view. So what can you achieve with that? And there are lots of promises of 3D integration. The first one is that you have a higher integration density, which I think you can easily already see with this pictogram in the middle. If you like stack dies, then your integration density will be higher because you have these 3D layers. You can also shorten interconnect length in general. because if you have a large chip, well, that's a large chip. You have to connect from one end to the other. But if you have stacked dies, then your interconnection length reduces. And it also enables novel 3D architectures, the topic of today. But there are also very daring challenges, and the three most important in science currently are thermal limitations. So basically layers in the middle, they run super hot. So that's really an issue because you can't get the heat out of your 3D stack. And as I said, TSVs require a lot of area, but also MIVs require area, and you have quite low yield for all of these integration technologies. And just to give you an example, I just said that, well, this enables novel architectures, and I just wanted to give a very, very broad and general example here that has been published in ISCA 2019. And here the idea was to do a 3D integrated processor, so designing a vertical processor in monolithic 3D. And what the authors did was that they took a look at the SRAM cells for caches and distributed them in 3D. And what you can see here is they got a 38% faster chips than 2D, and they consume 41% less energy. So you can see that with this very simple approach of actually just separating SRAM into two layers in a multi-core CPU, that you already can save quite a lot of power, and you can also improve the speed of your system. So this is the idea of 3D integration. And it gets more interesting for heterogeneous 3D integration, in my opinion. So heterogeneous 3D integration means that you stack dies in different technologies. So on the left-hand side of the slide, you see homogeneous 3D integration in a very simple pictogram. Everything has the same color. And if you go for heterogeneous 3D integration, the general idea here is that every layer of your chip can have a different integration technology. So here just depicted by different colors. So we can combine digital nodes with, for instance, mixed signal technologies or memory optimized technologies. And I hope that you can already now see where this can be of advantage for you. For instance, if you combine digital and memory optimized nodes, you can tightly couple memory, for instance, for caches with digital transistors for your core. So that's quite cool. I'm going to show an example for this at the end. So just to reiterate, the path from homogeneous to heterogeneous 3D integration is that 3D integration in general is like vertical stacking of multiple dies. So what you take a 2D design, you split it into multiple dies, and then you stack them and you vertically interconnect them. So that's what I just told you. And then this has some advantages, for instance, a smaller area footprint, shorter interconnection, lower power consumption. So this is like 10-year-old work and not that exciting. The game-changing innovation is now heterogeneous integration, and heterogeneous integration, as I said, is stacking of disparate technologies. And what does that mean? That allows you to integrate components with different demands for technology, and I would just like to highlight here the most two promising application areas. The first one are vision systems, so camera chips, where you can combine sensing and mixed signal analog-digital conversion and processing nodes into a single chip. And the second part is in general for high performance computing or CPUs that you can do an interleaving of memory and logic dies. That's quite cool. And Intel in 2019, they proposed this Lakefield architecture at Hot Chips 30. And so I took from their presentation just this very rough idea. So what you can see here is that they can remove parts of the CPU, integrate it into a different technology, into a different node, then, well, rearrange everything else, and then the base die is connected here. So I'm going to stop this because that was too fast in my opinion. So you have the base design with a 22 nanometer die where you have a homogeneous technology. So everything basically has to integrate it in the worst technology. And then the idea was to split it up into two parts. So basically everything that you can implement in 10 nanometer very advanced technology. For instance, the cores is here and the memory controller. So this is in this 10 nanometer die, but you keep the base die in this 22 nanometer technology where you include everything that is not able to be scaled that well. And then by this, you can see that this 3D stack is actually much smaller than the original design. So as you can see, it is already something that you would find in industry currently.
Hello, Dr. Joseph.
Yeah.
There's a question on the chat.
Yes.
Can heterogeneous integration be done in the monolithic manner?
Yes, heterogeneous integration can be done monolithically, as far as I know. So that's still under research. So people are trying this. Thanks for pointing out the question. But it's much more challenging to be frank here, because if you are doing it in a stacking way, I think it's quite clear. You just manufacture different technologies and you stack them. That's easy. For monolithic integration, it's much more challenging because you have to integrate different manufacturing processes into one overall process. So that's something you wouldn't find in industry yet. But frankly spoken, monolithic integration as a whole has not found its way to industry. So that's, I think, is okay for now. Thanks for the question. If there are more, just fire away. So I just want to show one academic example again, how to use this 3D heterogeneous integration. That's work from Professor Lim's group at Georgia Tech. And basically they took like a RISC-V core with level 1, 2, and 3 caches in a 2D design, and then they put it into this 3D stack. And what they did, they separated memory technology. So you can see the level 3 caches are on the lower layer here. And then SRAM for level 2 and parts of the level 3 caches in this digital node, with the core components here in gray. And they got quite a huge improvement in terms of area and performance here. So this is like the promises of 3D integration, heterogeneous 3D integration. So let's take a look at NoCs, and I just want to have a short integration example here. So our working hypothesis for all these works is that like existing NoC architectures do not fully exploit the intrinsic asymmetry present in heterogeneous 3D SoCs. So if you have a heterogeneous technology, your router network also has to be some kind of a heterogeneous network. And since heterogeneous, or I just want to go through the example first. So this is for a camera system, a 3D vision system on chip that we found. You can see you have mixed signal dies here. You can have digital dies. You can also have memory dies. And if we now interconnect them with an NoC, the idea is that the mixed signal dies, you will have different properties of your NoC than in the digital dies. And so basically you have two different kind of networks here, and the tricky part is how do we interconnect those two networks? And this is what we are going to talk about today. And in my PhD thesis, I called this technology asymmetric 3D NoC, because heterogeneous NoC was already taken, so we needed a different term. But the general idea here is to have an NoC that copes with the heterogeneous setting in this technology. And what are the most challenging integration issues here? So first, routers in digital layers are usually clocked faster, so you have non-purely synchronous interactions. You have limitations in these mixed signal nodes, so routers are just much more expensive there. You will have non-regular topologies because, well, your system is in a heterogeneous state, so your topology will be less regular than you would find in conventional systems. You have vertically heterogeneous links, so you need novel interaction schemes between routers if they encounter heterogeneous settings and different router architectures in two levels. And on a very physical design level, you also need heterogeneous signal drivers, because if you want to send signals from one technology to another, that's quite challenging. And today we are going to only focus on one of these, namely the non-purely synchronous interaction between routers. So the first work here that I would like to highlight is on, well, using heterogeneous router architectures. And yeah, it's just like the first work, and you can take a look at the paper that has been published on that if you want. So let's start with the basic introduction of the idea of the paper here. So the basic of the observation that we want to tackle is first that components of an interconnection architecture are non-purely synchronous in our setting, in the heterogeneous setting, since logic in digital nodes can be clocked faster than logic in mixed signal nodes. So this is the basic idea here is if you take any router design in RTL and you synthesize it for a digital node, and then you also synthesize it for a mixed signal node, what you will see is that the maximum achievable clock frequency that you can get for the same architecture will be different. And there will be specific numbers to that later on, but this is like up to 16x. So it's quite a huge factor of a clock difference here. So that's the first important observation. And the second important observation is that the feature size of individual identical components differs with technology. So if you take the same router architecture and again you synthesize it for two different technology nodes, one in mixed signal, one in digital, then your feature size of course differs, and by that also the size of your routers differ. And this is something we show here in this very, well, in-your-face type of pictogram, that in digital nodes, your clock speed can be faster than in mixed signal nodes. And also your feature size is smaller than in the mixed signal nodes. And this is these are the most two important characteristics of all these systems today, that the clock speed differs. So this is what we call this frequency gap, but also that the feature size differs. So basically you can, in theory, integrate more routers onto the same area if you want to, or you can integrate smaller or higher performing routers if you want to spend more area. So you have quite a diverse design space here. And for this work, the two major research questions that we wanted to tackle is, what is the influence on the propagation speed of packages in the network? And can we use the difference in propagation speed to improve latency? So our hypothesis was that if the clock speed differs between dies, then of course also the speed at which packets can go through this die will be different, and we want to use that for routing algorithms. And our approach was to first take a look at theory and try to model this. And I'm not going to introduce the complete model, you can find it in the paper, but I wanted to give you an idea of how you in general can design such a model, and also to give you an idea of how you can use things that you already saw in the lecture to define a model that you can then later on use in science. So that's the general idea here, because I know from the lecture slides that you already have had some of the modeling basics that I'm going to rely on here. So as I said, we want to model the propagation speed of packets throughout the network. And here the propagation speed, you actually have to think of it as like a speed in terms of meters per second. So how fast can data go from one end to the other? And what are the most important influencers on this propagation speed in context of technology scaling? So first, if you scale, if you go, for instance, from 90 nanometers to 45 nanometers, then you can achieve a higher clock frequency, as I already said, and I think that's quite intuitive for everybody here. And if the clock frequency of routers is faster, your propagation speed will of course increase, because you can work on these packages faster. But then there is an adversary to that, because if you do scaling again, you have a smaller area per router. So basically you can integrate more routers onto the same area, and this in turn reduces your propagation speed. So because I think this is also something that you should now be familiar with. If you have multiple routers inside your path, then each of the router will take a look at the packet, and this will reduce the propagation speed, because each router will have to work on the routing algorithm, the virtual channel allocation, and so on and so forth. The most important assumption that I made here is that you actually want to integrate more routers if you have the smaller area per router. This is an assumption that is not always the case, because you could also say if you reduce the feature size, you just want to increase like the capability of your core, but not the number of cores in your system. So this is something that is debatable, but if we assume that we just linearly increase the number of routers, that's basically like the worst case approximation that we can do here. So it is valid in terms of modeling, but it is a questionable assumption for an architect in general. So anyways, the important question here is, who wins? Does the clock speed win, or does the area win? And so for this, we wanted to go a modeling approach and try to understand this in terms of like theoretical considerations. So what we defined was a model that gives us the propagation speed of packets in your NoC depending on your technology node. And especially relative technology nodes, because we wanted to see in which technology is the propagation speed faster if you combine two technologies in a heterogeneous setting. So we found this we defined the relative technology scaling factor, and I think that's quite an intuitive definition here. So basically we take like the nanometer number of your node, like for instance 180 nanometer and 90 nanometer here, and you just divide them by each other. So I'm taking these very old technologies just because the math is simpler with, like, if you get 180 divided by 90, that's 2. That's simple, so let's just go for the old technologies here. For the sake of the example, it also works for more modern technologies in a similar way. So the idea of this technology scaling factor is that you basically take the 2 technology nodes and you divide them by each other, because that's basically what your improvements in scaling are giving you as a promise, what you can achieve as an improvement. And what can we improve? We can improve area and timing. That's like the 2 important factors here. So let's first take a look at the area model. So our idea was to again define this area scaling factor. And here again, the idea is to have a factor that describes the difference in terms of how much area can we save if we move from one technology to a more advanced technology. And this is shown here in the top right-hand side of the slide. So basically, if you have a baseline design, you have a part of the area that does not scale with technology, for instance, like power pads and stuff like that. And you have parts of the technology that scale, and these scale quadratically. So they get quadratically smaller if you have a scaling factor of 2 here in this toy example again. So these are like the 2 basic pieces of area that we assumed in our model. So this is what you can also find in this area scaling factor. So in the top hand side, you see that your area consists of one part of the area and the second part of the area. And then if you take a look at your quotient here, then you see that one part of the area stays constant. So this is like the orange area here in your figure. And then one part is scaled by this technology scaling factor to the power of 2 because it's an area. So this was our basic area assumption here. And then we thought, okay, does this model make any sense? So what we did, we synthesized NoC routers for different target technology nodes. So we first took a 180 nanometer mixed signal node because that was academically available for us for free. And then we took different digital nodes like 90 nanometer, 65 nanometer, 45 nanometer, and 28 nanometer. And we both used ultra low voltage and general purpose technology just to see whether this has a large influence on our model. And then we basically calculated the relative area savings here for these different technologies, but just by like dividing the size of the routers in terms of the synthesis results, and then fitted this model. And what we saw, and you can read the details in the paper, is that this fit was very well. So for our purpose here, this model holds quite well. And then I have to switch again. And then we also took the same approach for modeling of timing. And I think this is a little bit more tricky to model timing, because what you will see is that if you improve with scaling, then you can achieve higher clock frequencies. But of course, like, you can't do this unlimitedly, right? So otherwise we would have much higher clock frequency of any CPU nowadays. So what we did was we introduced this factor beta. So basically this gives us the maximum possible speed up that we can achieve. So in this setting, we said, for instance, that we want to have a maximum clock frequency of 5 gigahertz. We just assume that you will not be able to go faster than 5 gigahertz with your routers in general, just like by the properties of scaling and of power here. Because if you want to have a higher frequency, then basically your power budget would be too small. So, and then we thought, okay, so this is going to be like a saturation curve, and what works for a saturation curve? Something like this. So basically, we just tried out different saturation curves, and this one worked quite well in terms of model fit. So this is what you can see here for the timing model. And then you can see here again our synthesis results for maximum achievable clock frequency for the same NoC router. And then you can see that this gives like a nice saturation curve that basically saturates here with this 5 gigahertz for lower technology nodes. Okay, so now how can we model the propagation speed in our NoC? And for this, we took a look at the zero load model that you probably already know from the lecture. So basically a model where only a single packet traverses your network and there's no congestion. And we wanted to use a zero load model because we thought like this will give us the maximum performance difference for different technologies. And then we also need a notion of distance. And so for distance, we just took like a notion of distance, right? So that's just like our distance for a packet. So we take a look at the source node and the destination node, and we just get the norm here to have a notion of the distance. And then we can use this to basically calculate different latencies in your model. And I'm only going to show the horizontal latency for a packet here. And what you can see here in this figure, in this formula, what we do is that we take a look at this distance of your packet, Sn. So that's the distance your packet wants to travel. And we divide this by the density of routers. So basically, this gives you a notion of approximately how many routers will the packet encounter during its path. And then this is basically your hop distance, right? And then you have to add 1 because you want to eject the packet at the end. And then you multiply this with your clock frequency within your technology and the delay of the router. So how many clock cycles does a router need to basically work on one packet? So this gives you a notion of your packet latency. And then you can do the same, for instance, for the vertical latency, where it's much simpler. It's basically just a sum over different layers, where you again multiply the clock frequency of your router in the target layer with how many stages the router needs to, or how many clock cycles the router needs to process a packet. So that's basically your notion of defining latency. And within the paper, you'll also find a throughput model, but it works just the same. You basically take a look at these properties and then the clock frequency, and by that you derive your modeling. And then what we can see as a result, and I think that's quite cool, that we have this propagation speed omega measured in meter per seconds under zero load for an example 3-stage router. And then for 130 nanometer mixed signal technology, you get a certain propagation speed. But then you see that for different digital nodes from 90 nanometer to 28 nanometer were available for us for synthesis. So you can see that your propagation speed increases quite a lot. So this basically is a notion of the expected speed up from routing via a different layer. So that's quite cool. You have a heterogeneous chip, you have a digital and a mixed signal node, and then you see, wow, now I can use this to get a speed improvement. So let's use that for tackling latency limitations in our system. And so basically our general idea was, let's do something quite similar, so simple here. So if you take a look at your 3D stack, then let's say you have a 180 nanometer layer and a 90 nanometer layer. So one layer is slower than the other, basically. Then the numbers don't matter here that much because it's just the relative offset that matters. And if you use standard XYZ routing from router 1 to router 2, you would take the top path and then go down. And on the backward path, you would go down in the bottom layer and then go up at the end. So that's your basic XYZ routing, where Z is the last dimension that you minimize. But in our setting, we said, okay, that's bad because this top layer will be slower. So let's route the packet over the bottom layer in both cases. And we called this Z plus XYZ minus routing, and we saw a speed of up to 6x here, depending on your distance between two routers and your technology settings. So in colors, you have different technology settings. And of course, if your technology difference is larger, so your mixed signal node scales much less than or much worse than your digital node, you will have a larger speed up of this approach. And so this was quite nice, and basically it has 0% area cost versus XYZ. And then you can also take a detour via the bottom router, so that bottom layer, so that's also possible. And then, of course, you don't always get a speed up because you have a detour, so you will have to go through more hops. But as you can see, there's a certain threshold after which it's worth it. And we saw up to 1.7x improved latency for this routing algorithm. So that's quite cool, but it yields one important issue here. And this is why we need a co-design with the router architecture. It basically yields the issue that if this router wants to talk with this router, the bottom router is clocked faster, and this limits your throughput in your system. So basically, for every system where you have throughput, your chain is only as strong as the weakest link. So as you can see here, if you communicate from your slower layer to the faster layer, it doesn't matter that the faster layer is clocked faster. It can't work on packages faster because basically they are not fed into the faster router at the higher clock frequency. That's not what should happen, but anyways, so our idea was that we want to basically have larger packets at the top layer, and these we call high throughput packet transmission. That is transmitted at the slower clock frequency, and then we can split these up into multiple smaller splits in the bottom layer. Sorry that the figure was removed here, but yeah, that's an issue. So so this is why we need a router co-design here for the routing algorithm. And so we achieved this by taking again a look at the routing algorithm. I'm just going to go back for 1 second. So what you can see here is that the communication pattern from the top layer to the bottom layer, if you want to actually have a heterogeneous route, so a route that goes through both layers, it always is from the local port downwards or from the downwards port to the local port, and here the same holds. You would never go from any other port in the router than the local port to a downward or upward connection. And so this is what we used for the modified router. So we said, okay, the downward, the upward, and the local link, they have to be modified to hold these high throughput packages. And then we changed the crossbar in terms of one part of the crossbar that connects down, up, and local here. Can hold like multi-flit transmissions, and the rest of the crossbar only can hold single-flit transmissions. So this crossbar has n bit width, and this crossbar has CF n bit width, so clock factor times n bit width. And this is basically the idea here, that if we have a larger crossbar, we can transmit multiple flits at once, and by that virtually bridging the frequency gap. And then we also need to modify the input buffers. So basically you need a shift register that takes in packets at a faster clock speed, and then you read them out in parallel into the input buffers of your router. And you can also do this, so you can either do this in the faster layer and have multiple TSVs or MIVs to transmit the data, or you can have it in the slower layer but clock it with the clock frequency from the faster layer. So these were the two technological options that we found, and downwards it's quite simple. You can just basically feed it in parallel and then read it sequentially at the higher clock frequency. So this was our general approach here. And for this, we could see that we had a throughput increase of 2x to 4x at different costs versus a baseline XYZ router. And we could actually reduce the costs, because if we use this kind of way of routing, we also see that our path diversity is reduced, and using the reduced path diversity, we could further reduce the router logic. So that's quite cool. And we also took a look at a real-world case study here. So the idea here was to use a 3D vision system on chip, which I already explained that this is one example application for heterogeneous 3D integration. And you can see our case study on the right-hand side here, where you have an image sensor at the top. You have a mixed signal layer with ADCs, so analog digital converters of these data from the image sensor. And we also, for the sake of the example here, put in some analog accelerators inside. So basically acceleration units that can do analog computing like memristors. And then we have two digital dies which have GPU cores and CPU cores. And as you can see, we are using 30 nanometer and 50 nanometer node here. So this is like actually an example with well-scaled technology. And then on the left-hand side here, you see that everything is a little bit described, but I think the two important points are especially the application. So we assume that the image sensor records at 720p, and we want to do a face recognition algorithm on chip with Bayer filter, Viola-Jones, Sheehan, Tomasi, Candelucas, and Tomasi algorithm. So basically like the whole image processing pipeline of your face recognition algorithm. And then we took a look at the routers, and for the digital layer we assumed a 1 gigahertz clock frequency, and for the mixed signal layer a 0.5 gigahertz clock frequency. And then what we can see is that our throughput increases by 2x. The average latency of flits in this case study is increased by 2.26x. The area is increased, unfortunately, by 2%, but I think that's fine for this latency improvement. And we also have dynamic power savings of nearly 40%. Using the aforementioned routing algorithms. So in my opinion, this is quite a successful way of approaching this frequency gap. Okay, so let's go take a look at the second example that I have brought to you, and this is the class project from last year. And we submitted this to ASPDEC this year, and you can see that also you can take a look at the paper, which is already have been published. So, as I already said, what are the two most challenging integration issues? And here I'm just repeating myself, but let's do it for the sake of the example. We have varying areas between routers, which can be exploited to improve area, and I have some references on that. and we have this varying clock frequency. And now we again took a look at these different synthesis results. So we again have here this clock frequency factor versus a 180 nanometer mixed signal technology, and then we have different digital technologies put aside here. And what you can see is that we actually can get up to approximately 16x frequency gap. So that's quite challenging. And this has there's a large frequency gap, and that limits performance of the NoC. And so in the last solution that I showed you, we had this router co-design, which is a valid approach, but it is really, really complicated, right? So can we do something else? And the idea of this work is now to go to a network architecture approach. So what are the two consequences of this frequency gap? Well, the flit latency varies and the throughput is limited by the slowest router. So these are like the true important consequences that you already know. And basically we have three potential designs to go for this. So first we can use homogeneous synchronous routers. If we use homogeneous synchronous routers, we clock everything at the slowest clock frequency, and this basically limits your latency and your throughput. So I don't really like that. That's not the best you can do. Okay, so let's go for an asynchronous approach. So here the idea is to basically clock everything as fast as possible, and it's fine that routers are asynchronous. You can just use like any asynchronous or synchronization approach between routers and use that. So here we call this homogeneous asynchronous routers, and this, while it improves latency.
Hey Moritz, just to interrupt, I do want to mention, maybe I should have mentioned this earlier. So officially the class goes on till 1:15, like 1:15, it's a 45-minute thing. So we're kind of at time, close to end of time. But you know, feel free to go on. If students do need to drop off, you know, they can just follow up and listen to the last piece because it's recorded. But if the students can stick around, I think that'll be great. But just wanted to kind of give you a sense of time.
Yeah, I think I should be finished in 15 minutes with the content part, and then we can go to the class project. So, yeah.
Oh, sorry, my bad, Alex. Oh, sorry, this is just me kind of completely. Okay, so this is me jumping between meetings and not. Thank you, Alex. We have half an hour more. My bad.
Yeah, I think you're fine.
Yes. Okay, we have a lot of time. Go ahead.
So I see two.
Sorry about that. Yeah.
Okay, we have until 1:45. Yeah, so I think that's fine. Okay, thanks. Anyways, okay, so I was talking about these different router architectures, and the basic idea was here that homogeneous synchronous routers are bad because we are limited by the slowest clock frequency, and if we go for an asynchronous approach, while we improve latency, our throughput is still limited, and we also need like physical design effort to do the synchronization logic. And so that's also not the most or that's also not a very good solution, right? So then we can use this pseudo-mesocronous routers. That's basically the work I just introduced. And okay, that can improve throughput, but now I'm bashing my own idea here that I just showed you, but like stick with me. I think that's a very valid argument here. So we have to use these non-standard routing algorithms, so non-XYZ routing, and that yields a very skewed, load on different layers. So what you can see here is that this is the traffic load of the digital versus the mixed signal layer. And depending on the threshold for the detour of your ZXYZ routing, you can basically see that your load is something like 500x higher on the digital layer. And no NoC will ever be able to cope with that. So depending on your technology setting, this might be a deal breaker for you, that this higher load on the digital layers actually is not acceptable for you. So we want to do a novel approach, and the idea here was to go for heterogeneous routers. So basically change the router architecture on a network level. And so existing solutions are either limited by the slowest clock frequency or yield an area overhead for synchronization. And yeah, heterogeneous synchronous routers might be a solution here. And the simple observation that I think is kind of trivial, but very, very promising here is that VC-less routers can have a higher clock frequency because you don't have to have everything regarding virtual channels, right? So we analyzed that for like a set of technologies here with the students last year, and what you can see is for a router without VCs, we can achieve a higher clock frequency than for a router with VCs. So that's quite cool, right? Because now we can use some of the routers without VCs in our slower technology, but we can accomplish them with routers with VCs in the faster technology, and that sounds like a good idea. I thought, and actually it does at the end. So what are the different NoC architectures that we have? So the baseline is that we have a homogeneous architecture. So in the homogeneous architectures, everybody has VCs and they are clocked synchronously, right? Okay. Then we can go for the asynchronous approach. Again, everybody has VCs, but everything is clocked as fast as possible. So 2 gigahertz in the digital node and 0.5 gigahertz in the mixed signal node. Then the pseudo-mesosynchronous routers that I just introduced has a heterogeneous network architecture because the routers look different, but everybody has VCs. So in terms of the VC architecture, it is the same. And then again, we can clock at integer multiples of the baseline clock frequency. So here we can clock again at 2 gigahertz and 0.5 gigahertz. And our optimized design that we want to use here is using a heterogeneous network architecture and is clocked synchronously. So basically, we are using only one VC in the mixed signal node. Then we can get up to 1 gigahertz maximum clock frequency here. And then we underclock the routers in the digital layer, but we have a synchronous design, which reduces the design complexity quite a lot. And I think the only last interesting question is this worth it? Is this idea worth it? And this is something we analyzed. So we first took a look at power, performance, and area for an 8x8x2 NoC with 4 VCs, 16 flits per packet, XYZ routing, so just some random parameters. And we compared TSVs, MIVs, and face-to-face bonding. And so what you can see here is that versus the baseline design, so the homogeneous design, we can save area and power, but we will have a higher average frit latency for uniform random traffic. For the asynchronous design, again, we can save area. We were not able to estimate the power because we didn't have any synchronization logic at hand to synthesize it. So we basically couldn't claim any numbers on power, any useful numbers. But we were able to improve the average frit latency and also the throughput. So that's quite cool. And versus the pseudo-mesosynchronous design that I proposed before, again, we were able to save area. For power, the numbers were not reliable, so let's not discuss them. But we saw that our design has a higher average frit latency, which is bad, but also we don't have any better throughput. So in general, like in terms of our power and area, that are really, really nice results. So that's good. In terms of flit latency, that's somewhat ambiguous. So we don't really know when it's better or worse in this design. And in terms of throughput, we achieve something. We are better in 2 cases and similar in 1 case. So that's actually an achievement here. So let's take a look at this flit latency because that looks interesting, right? So we first took a look at power and area for one short example here. So if you have more VCs in the baseline design, of course you save more area by removing VCs from one layer. That's simple. And in terms of power savings, we see the same again. But if you have a 2 VC setup in the baseline design, it's not worth it. So it's only worth it for 4 and more VCs. So that's just on a note here that you know that it's not always worth it. But so let's take a look at performance. I think that's the much more interesting part here. And so what we did was, again, we took a closer look at the uniform random traffic. And so we made a sweep over multiple injection rates here and plotted the flit latency on the x-axis. And we have 4 designs here, the conventional design, so basically the homogeneous synchronous router. Then the asynchronous routers where everybody is clocked as fast as possible. Then we have the pseudo-mesosynchronous router that I introduced before. And we have the optimized architecture, which is with the heterogeneous design. So this is like the purple one is our target design here. So what you can see here is that we outperform 2 of these designs, namely the conventional approach. So you can see here that it saturates earlier and has a higher base latency in this setting. And also this pseudo-mesosynchronous router has a higher base latency and saturates earlier. So we are outperforming those 2 designs. But we are not faster than the asynchronous design. So your asynchronous design, as you can see here, is consistently faster over the whole injection range. And we saw this for all kinds of different network settings. So we investigated different network sizes, different number of VCs, different flit buffer depths, and different number of packets per flit. And we saw this consistently. So this is like a consistent result that we are worse than the asynchronous design, but better than the other 2 designs in uniform random traffic. So as you can see, the baseline and pseudo-mesosynchronous design are 20 to 47% slower, but the asynchronous architecture is 6 to 41% faster. So from this perspective, it seems to be that you basically want to go for the asynchronous architecture. It seems to be the best option here right now. But keep in mind that we had quite large area and power savings, so we are much cheaper than the asynchronous architecture. So this is actually a design trade-off that you have to think about. Like, is it worth to achieve 6% faster flit latency by having 50% more cost? So that's up to you as a designer, but that's the story here. So we also took a look at parsec benchmarks. So this is like, I don't know whether you know this. This is a multi-core benchmarking suite with different benchmarks that you can see on the x-axis here. And on the y-axis, we have the flit latency, again, normalized to the optimized architecture. So our optimized architecture has a latency of 1 here. And then you have, again, the 3 other architectures. So what do we expect here? We do expect that the conventional and the pseudo-mesosynchronous design are slower because they have been slower on the slide before, and that the homogeneous asynchronous design should be faster. This is like our expectation from the Eurond results. And this is actually something that we see, right? So you can see that the blue and purple bars are always higher. So since it's normalized to our architecture, it is worse if you're above it. So this is what I've written here on the right-hand side. So we have a worse performance versus the baseline and the pseudo-mesosynchronous design. So this is in line with the results from the previous slide. But we have ambiguous results for the asynchronous architecture. So you can see that the asynchronous architecture for some designs is super fast, which is quite cool. But then especially this WIPS benchmark showed that it has similar performance and sometimes even worse performance in the asynchronous case. So this is a really interesting result. So long story short here, if you compare against the asynchronous router, you have to take a look at your specific application pattern, whether your asynchronous design will yield better performance or not, and how much better performance you get, because this impacts your decision on the area and power trade-off. So as you can see, we just reiterate here for overall like different network settings that we tested, we have something like 60% improvement versus baseline, 30% to 60% improvement versus the router I proposed before, and ambiguous results in terms of the asynchronous router. So to summarize this, and this is like the last content slide for this, so we can compare it against those 3 designs. So against the homogeneous synchronous design, we are better in area, we are better in power, we are better in flit latency, and we are better in throughput. So that's like a very clear indication that our approach is valid and quite nice. Versus the asynchronous router, we are better in area and power again, but we are sometimes not better in terms of flit latency. So here it depends on your application pattern, but we are better in terms of throughput. So that's also something I think quite important to consider, that throughput increasements are achieved. And you don't need any synchronization logic with our design. So this might be a consideration for you, that you say, okay, I really don't want to care with asynchronous design. That's complicated. Don't bother with that. So this is why you might not want to go for an asynchronous design. And versus the pseudo-mesosynchronous router, we are better in area, we are better in power, we are better in flit latency, and we achieve the same throughput. So in my opinion, this is a clear improvement versus the architecture that I showed before. Also, we have a reduced number of vertical links, an improved yield, and we have fewer clock regions in the design. So there are quite a lot of advantages of this design. But there's one major drawback, and I think this is really important to keep in mind. If you have routers without VCs, you are losing all the advantages of having virtual channels, for instance, for deadlock freedom. So in some cases, it really depends on your use case. You actually might not be able to go this route, and this might be something you just don't want to do, right? So yeah, that's the story of these routers, and I'm quite happy that with the students from last year, we were able to publish this and really also bring it to a very nice paper. I think it's a really nice written paper, and I'm quite proud about this work. So yeah, that's it in terms of